Welcome back from lunch. Hopefully you were able to fight through the two conferences at once level crowds to actually get some food. I'm very pleased to welcome our first speaker after lunch, Animesh Garg. Animesh is a Stephen Fleming early career professor right here in town at Georgia Tech, where he leads the People, AI, and Robotics Lab. His research focuses on understanding structured inductive biases for learning and causality for decision making. And today we're going to hear about an agentic perspective on long horizon robot planning. So, thank you.
Thank you. Okay. So to keep up with the spirit of workshops, I would love for you to ask questions. Feel free to interrupt me however much you want. I do not need to go through all of these slides. We'll pause wherever we are. That is the point of this. Okay. This is something that I've been thinking about, and to be frank, I always thought that low-level skills is where a lot of the challenge was. But when these things started a little more working, we realized that a lot of the cognitive reasoning, at least the way they work, we don't have a lot of infrastructure for generalizing that. So I've been for a very long time trying to push for this idea that we need generalizable frameworks. You cannot train for one particular task in one particular domain, and it won't work broadly. So a lot of the ideas that I've been having was maybe what we can do is we can think of these problems effectively as pre-trained models or foundation models, if you will. But the idea is that you separate what you would call the what and the how. Right? So you can imagine that you have a high-level model which can do reasoning or understanding, and then a low-level model which actually generates the motion per se. Right? And this, by the way, I do want to point out that this is not system 1, system 2. The low level itself can be system 1 or system 2. The low level, if it's reactive or policy, it's system 1. If it's actually deliberative and online planning, it's system 2. It's really basically bifurcating the problem in what you would call high-level cognitive reasoning versus motion generation. So what I'm going to do today is I'm going to talk about a few what I would call recent problem settings in this domain we have looked at. And they're slightly different in terms of assumptions, but they are very related. So I want to think about this problem in what you would call two ways. You can argue that we have simple skills, but the planning problem is complex. You actually have to do reasoning. Or on the other side, you might say the skills are complex, but the plans are kind of simple. Right? And within each, the first assumption we were assuming, which is more standard, is skills are given, can you do planning? But we make this assumption that planning domain is not given. So you have to plan, but the planning domain hasn't been specified. Now, can we extend that idea to skills or learning skills along the way? On the other side, let's assume plan is given, but it fails upon contact. The skills are not reliable enough. So what do we do in that sense? And then finally, can we just scale the idea of learning these skills or general purpose skills with foundation models, except without the foundation model scaler? So that is the setup of the talk, and let's get started. So let's talk about the first problem, which is planning, where planning domain is not provided. So the idea of language models to planning is something that I have been thinking about for actually before language models were a thing. So we used to do this work called neural program synthesis, neural task programmers, and neural task graphs. So we were using I would call RNNs to output effectively the next action or the next skill to call and the argument to call it with. So when GPT-2 and GPT-3 came around, this is before ChatGPT had happened, we were absolutely excited. Like, this is it. We have to do it. So at the time, I think there were two groups. One was me and my collaborators, and then I think the other group was at Google. And basically, two groups came up with a solution that I would argue is kind of similar. We came out with something called proc prompt. They came out with something called code as policy. The idea was you feed in the representation or the setup of the world to the environment or to a language model, and the language model outputs something that is Pythonic. It doesn't output Python, and then you can, in general, execute this. And this was simplified and at the time very exciting as well. But obviously, arguing that a language model can plan is equivalent to assuming that it also is a general purpose computer, which I would argue it's not, right? You're basically saying that would an LLM be an executor for an arbitrary program, right? Let's say if I ask your LLM to output factorial, maybe 2 would work, 4 would work, 6 would work, maybe it has cached, but 1729, it is not an actual computer. It has to output something. Planning, to me at least, is the same problem. Planning is a search problem for which problem instance is provided. Learning model can speed things up, but it cannot be a general purpose plan. So then that led to this idea that, hey, if that is the case, then maybe instead of using the system as a planner itself, we should be outputting the domain and then the definition. And basically use our planning algorithm with some sort of initialization. And then the fact that we now have a domain, we can actually do more interesting things like verification. So that led to this idea that we call it CLIMB, which is basically this idea of continual learning of the planning domain itself. So the core idea was that we want to start with simple domains, and you learn a PDL model effectively of a particular domain. And as the task gets more complicated within the same domain, often what happens is the domain definition file is not changing because the affordances are roughly the same, object next to object, or the classifiers or the tests for these evaluations are the same. What is really happening is the task definition often is changing. And that was the idea that as the complexity increases, the world model should be incrementally learned. And at some point, you should not need more data. It should become zero shot by virtue of it. But when I use the word, or when I'm using the term world model here is not the dynamics model. World model is literally the domain definition file, right? So this is the idea. The idea is you start initialize with some natural language description and some atomic skills. These skills basically are now generating domain knowledge, and then that results in a plan. But because it's an LLM, the plan may not always work. Some skills may not exist, so you might need to add new skills as the system tells you when the system fails. More interestingly, when the plan fails, you can use the failure directly with a VLM to tell you what failed. And this allows you to effectively update the world model or the domain. That is the core idea. So what does this look like is explicitly you input to an LLM in a zero-shot manner some sort of language. The output of this LLM is first the domain definition file and the predicates and the grounding of those predicates. You can now check these predicate grounding with a VLM. So there is no human in the loop per se. Now you have a symbolic planner that can actually output a plan with the domain definition that you can execute and observe. Depending on the observation, either it will work, or if it will not work, you can actually have what you would call what didn't work, and that can be fixed. And the fix is actually an addendum to your file, right? So let's start with a very simple example. You want to build a pyramid out of 3 blocks. You start with some initial model. The plan is pick up B1 and stack B1 between 2 blocks, right? Now, well, the robot actually does stack B1 between 2 blocks. You never said that they had to be actually adjacent, right? So then that is a fix. It failed because that you're missing a predicate. So then you fix this predicate, you fix the model, and the new plan actually says, do the right thing, and now it'll actually put the red blocks absolutely next to the red block so that you can actually build the pyramid, right? And this is just an example of a very simple example of what a fix looks like in a single stage. This fix can be multi-stage fixes, and you can iteratively keep doing it. In fact, we found that you start with simple environments. Initially, zero-shot performance is very similar to your favorite LLM, but very quickly, the LLM stops failing. And at some point, we find that we just don't need data. We are done because these domains are simple. You don't need to keep defining the same thing over and over again, right? while an LLM actually stops working. No amount of data works. Like you can give hundreds of examples and it still doesn't work. We are basically working with nearly zero shot. I think there was a mistake here. Y-axis should be bounded. Y-axis is actually just 1, 2, 3, 4 demonstrations. So very little data. Okay. So the takeaway in this case was LLMs are really good at code generation. And what we made them do is we made them output code in the form of PDD. Okay. The second part was this idea of agentic frameworks. So this is something that we were stuck with. We were working on many of these sort of problems, but we found that LLMs were very good at this. But when they were applied to planning, reasoning never worked. So we created a new benchmark where reasoning was required visually. So this is a very simple example. For reasons of contrast, it's not visible. The task is very simple. Put the block in the cabinet. But if you notice, the cabinet has been, by design, created sort of an abstraction. So there is no simple plan that will work. You actually have to understand that it's not that the plan is wrong. You actually have to do something additional beyond the plan that will work. Right? And that is not in your domain. So in this case, we are not using domains anymore. Everything is LLM. And there is no notion of what you would call causal reasoning or exploration. And that is the problem we were trying to solve. In zero shot, of course, they failed. So a GPT-4V at the time failed. And we have actually updated this. This problem is actually fairly interesting. The problems are deceptively simple and yet not solved. So what we do is more like what you would call these days an agentic architecture. It's a 3-level architecture. In this case, neither the model at the high level nor the skills are known. High-level planner creates a plan. Each plan then basically creates a sub-plan. And each sub-plan then generates the cost function for which you will solve the MPC for. So you're basically generating the whole thing end-to-end in an iterative manner. And then there is a VLM which tells you at the low level, is the skill complete or not? I'm not going to go into details of this agentic architecture, but you can imagine that there is a high-level, 5 big feature components of high-level planner, a VLM perceiver, which is basically going to inform at every level, a low-level LLM planner, which is planning at subtask level, a motion generator or motion feedback controller, and all of this is wrapped into a LLM verifier. Right? So verification allows. So now you're basically doing planning at all levels simultaneously. Okay. What kind of problems we can solve? So the example I showed you, this is an example. So what happens is, this is a trace of what looks like. You said, pick up the yellow cube, open the cabinet, but can't open the cabinet, stuck. So need to do replan. Now, replanning happens at the highest level, not at the motion level, because motion level is fine. So now you basically say, you need to move the red block out the way. How do you move the red block out the way? You basically go to the block, put it away, and then go back to the original plan and continue, right? So this is skill constraints. You can have semantic constraints. I said, find the green apple. I didn't say where it is. Right? So you should automatically know what are the things that are openable here. So it automatically says, okay, find the green apple, look inside the green cabinet. Looks like a good idea, right? So you try a green cabinet. Turns out, I'll fast forward it. Turns out there's no apple. Then we'll be like, try the next cabinet. No apple. What do you do? The other thing left is the microwave. Then, well, it turns out microwave is not openable because there's something in front of it, right? And then you move the thing out of the way so that you can open the microwave. And then if you see the object, then you're done or get to the object. You can do all sorts of interesting stuff. So we created this puzzle. Let me pause this. The puzzle is very simple. The task is open the stone cabinet. We don't tell it anyone. So this is one of those tasks which was inspired. I was inspired by this idea that when you go to one of these office doors, you have to use your key card. But no one tells you you have to use your key card. You just know that this is there, must be used. So it was like this. So the green thing is actually a sensor on which you have to put a weight. When you put the weight on, the stone cabinet unlocks. Otherwise, you can keep trying, it will not move. The green and that weight can be anywhere in the environment. This requires semantics. Right? So this is kind of planning, but you're actually planning at a high level. So now you actually have to you have to do other things to now figure out, okay, take this object, put it on the green thing. And it's an example of semantics. You can extend this. You can basically say, you put the red object on the green plate, and then the stone cabinet opens for the next 30 seconds only. This actually happens, right? When you tap your card, your door is only open for the next 30 seconds. And then you have to do this. Now the door is unlocked and you can actually card. And all of this is by feedback. The system is not like knowing ahead of time that the door is locked, right? It didn't work, hence it tried the next. Same example here. The door is locked. The lever needs to be turned down for the door to be unlocked, but we didn't say anything at all. So the LLM or the VLM has to figure out like, okay, if the door is not opening, what other objects can I interact with? That would make sense, right? And you can keep extending this. So in this case, when it doesn't work, then the next interactive action is to operate the lever. Please note, in this case, all motion is generated by generated rewards. So there is no pre-coded motion. There is no pre-programmed skills at all. Yes, question. Surprisingly, not a lot. It just is slow. Slow in the sense, high-level planning, it takes time. It's usually of the order of like a single-digit number of trials because the number of objects is very few. So the VLM is very good at figuring out, okay, if this is not working.
Sorry, briefly, for other questions, please come to the mic at the center so folks on Zoom can hear you too. Thank you.
I'll skip because in interest of time, well, I can show you the numbers. The numbers are, basic numbers are, GPT zero shot does not work at all. GPT-2 rewards or Eureka-like models, which is basically let me predict rewards, work on very simple tasks. As the tasks go hard, which require either reasoning or search, they fail. And then you basically have to do additional replanning is requiring, VLM is required, and verifier is required. Yes, tasks. Please, I'll repeat your question. Turns out, hallucinations were much more of a problem in 3.5, less of a problem in 401. Answer one. Two, the domains in robotics surprisingly are much simpler. LLMs do hallucinate, but in very complicated domains. These are very simple domains. Like if there's one object, one lever, hallucination is very little. We have actually, I don't have video here, we have actually applied these ideas to much more complicated domains like actual chemistry lab automation as well. There you have to add a verifier to ensure that the LLM is not outputting, let's say, actions or entities that don't exist. So for example, move beaker 1 to beaker 2, but beaker 2 doesn't exist. So that verification does help. So it allows you to create. So there's some sort of implicit thing that I didn't say. When we do planning, we use a technique called clarify. When you're doing iterative planning, in this iteration, we are effectively doing what would now be called RAG. So you're constraining the generation to a particular set of what you see rather than anything. Also, a lot of this, because the world has been moving very fast, what used to happen was LLMs and VLMs used to be very separate. I would say as of early last year. Meaning VLMs were not good at reasoning, LLMs were good at reasoning. VLMs were good at, well, image understanding. And now I think of late, you get best of both worlds in a single model. So the kind of hallucinations that existed, let's say fall 23, don't exist anymore.
I can actually ask a quick follow-up.
Yes.
Do you find that performance sort of grades smoothly with task complexity, or is there like a sharp cliff where suddenly these things just stop working as the task gets to a certain level of complexity?
That's actually a very good point. To be very honest, we have definitely evaluated this in the early complexity sort of types where simple solutions don't work. We haven't gotten to a point where my idea was to create escape rooms. We haven't created escape rooms where this has failed. So the kind of tasks we have in the benchmark about 5 to 8 step puzzles, meaning it's not just a single step puzzle. From a planning perspective, it would require 8 independent steps. That seemed to work. Perhaps if it needed more complex things, my hunch is if the low level skills were truly stochastic and it worked only 50% of the time, that is when it will be very interesting. Or the failure modes were of very many different types. So now the one thing that I do want to talk about, and I'll then pause, is in many cases we did realize that we could do planning, but the magic trick was low-level skills were as long as they were pick and fix. If all of your low-level skills look like go to, grasp, go to, place, then you can do interesting plan. But if you needed to do anything more, it would get stuck, right? So this was something that we were stuck at. Like, how can I really sort of energize TAMP with low-level skills, but skills being learned rather than specified? So for example, if you want to make coffee, you can run your TAMP planner and you can basically say it's multi-stage plan. But then we were saying, how do we improve this? Because all of these skills cannot be hard-coded ahead of time. So what we said was, for every section you can say, okay, there are parts where I can provide behavior cloning. There are parts where I can use task and motion planning, because let's say go-to is very easy to use task and motion planning. But let's say if I have to interact with the knob, it's probably easier to provide BC or behavior cloning. And then we said, probably BC requires a lot of data. We can actually run RL with fine-tuning at only these times. The interesting trick is you use RL, but not for the whole thing, only places where you need RL, where basically the rubber meets the road. Otherwise, you're doing motion planning and it works very well, right? So effectively, you have human demonstrations, you have a BC policy. We limit the demonstrations to be very low, so the BC policy may not work. So we train a residual policy on top, and that basically results in an RL policy. And then you get basically a fine-tuned policy for even contact-rich tasks. So now this is what final steps look like, right? So you have a task planner which says, put the cup under coffee machine, open the coffee machine, open the drawer, get the coffee pod, put the coffee pod in the coffee machine. I'll play this again. Every time you see the red border, RL is the policy that is active, right? And every time robot is just doing motion planning, the red border goes away, right? So every time the interaction happens, we add RL for very good, what you would call contact condition. So one takeaway was, it results in much more robust policies than either pure BC or pure RL. So you can actually get it much better. RL doesn't even solve half the problems to begin with. We can do this with very small data. So we can do it with 10 demonstrations, what BC cannot do with 200. The quality of the solutions is very good because RL well overfits. So RL does find solutions that are like faster. The interesting thing is we don't need BC policies that work. We need BC policies that work 5% of the time. So we can convert a 5% BC policy into a 95 or a 99% RL policy. And importantly, it is a multi-stage policy. And of course, I think I already said this, that not only does it improve completion time, so RL, pure RL can have dangerous behaviors because reward is not always tuned correctly. But because we are using BC guided RL, it actually preserves safety very well because you can always tune down. One more thing that I do want to say, and before I take questions, is in this case, RL does not need reward. RL is 0-1 completion from TAMP. So we only use BC data to get this information, and RL is done in pure image. Okay, I think I can carry on to the last point or take questions. So let's do that.
Yeah. So I have a question. You have a planner that sequences these skill components. Is it able to like handle like do you have to like sort of funnel to make sure you are in the right initiation sets to execute the next skill?
Oh yeah, I didn't talk about this in the step time. Basically, when you're doing RL for multi-step planning, so the planner and RL are running in what you would call interleaved manner, so that initial state distribution for the RL is actually driven by the planner rather than randomly sampled.
So if we had like a gremlin that interrupted the state of things, would the RL be able to like recover and then continue its path?
RL would be able to recover if you were within the let's say skill region. If you were in the planner region, let's say if the task is being moved and then you grab that robot and move away, RL has not even begun. So this is not something that is like under the purview of RL yet. As I said, so the final policy, as I said, is an interleaved policy between a planner and a motion, or policy and a motion plan.
Thank you.
Right. I'm sorry to cut off your question. Animesh will hopefully be able to stick around for the panel later, but let's thank him for a very interesting talk. And for time, we're going to move on to the next speaker.
Cool.
So please, let's give Animesh a round of applause.
Thank you very much. While the next speaker does set up, I do want to leave you all with one lesson, though. One thing that I learned with this exercise was, feel free to set up, is LLMs and VLMs are surprisingly good and can get us very far with zero shot if used properly in the agentic frameworks. The idea of using them correctly is still very early on and is actually a scientific question that I hope this community will explore. Thanks.
All right. Thank you so much.